I'm recording meeting as known. Okay, is there anything in particular you would advise us to pay extra attention to for the exam? Nothing really. I will have some examples, but they are just examples. Obviously, should pay attention to them, but nothing really special. For the free response questions, how do we represent triple and double bonds when typing out a condensed structural formula? Double bonds are easy. That's equality sign. For triple bonds, there should be a special symbol. You should be able to copy and paste a symbol from a Word. So here are few questions that I have prepared for the review session. When I post the video, then when you watch the video, you can of course pause the video and read these questions and do them if you wish on your own. So first to deal with incorrect name and then converting it to correct name. So first one is 4-propyl-2-ethylhexane is an incorrect name for a compound. What is its correct name? So this is frequently something that gets students confused, and some students don't even bother to answer it, even though it's a relatively easy question. So what you need to do is, of course, you need pen and paper, and then you need to draw a formula. Draw a formula from the name. Just because name is incorrect doesn't mean that it does not correspond to one single compound, and that you cannot draw a formula from it. So what you do is, I will use chemistry drawing program, but what you should do is pen and paper, and from that name draw a formula. So, I'm supposed to paste this name. Okay, so here it is. 4-propyl-2-ethylhexane. So simply from this name, even though it's wrong, you draw a formula. So hexane, that means parent chain is hexane. 6 carbons. On carbon 4, there is propyl group, so 3 carbon units. So it's carbon 1, 2, 3, 4. So there should be a propyl group. Okay, let's put it down. May not be the best drawing, but okay. And then on carbon 2, there is ethyl group. So 1, 2, 2 carbon units. Yeah, but this is a bit too high. So I can do this propyl group now a little bit better going up. Again, you would do it with pen or a pencil. So now you can probably see what is wrong. What is wrong is that hexane is not the longest chain. The longest chain starts here, so it would be carbon 1 and then carbon 2. You should number them again, maybe writing down the numbers 4, 5. You may have to look a little bit different paths, different chains to see which one is the longest. For me, it's easy to figure out which one is the longest chain. So you can see 8 carbons is the longest chain. So that means that this is not hexane, this is actually an octane. And now be very careful, once you figured out it's octane, what are the substituents? Because sometimes students figure out, well, okay, it's octane, and then come up and then use same substituents, ethyl and propyl. No. On carbon 3, substituent is methyl, and on carbon 5, 2 carbons, it's ethyl substituent. So it's ethyl and methyl, and you list them ethyl first. So you list ethyl first, and ethyl is on carbon 5, so it's going to be 5-ethyl. And then you list methyl second, it's on carbon 3. And it's octane. And that's the answer. So as you can see from wrong name, you can still draw a formula and then come up with correct. We like to ask questions like these because in a single question, we test two things. We test, can you draw a formula from a name, even if it's wrong, because same rules apply. And then from formula, can you come up with a name? Can you name the formula? And so that's why these questions are pretty good. And then second question, my computer is a little bit slow, is about naming of an alcohol. And let me see. So that's 2-chloro, 2-methyl, 5-hexanol. So again, from this formula, you draw a compound. So it's going to be hexanol. Again, 6 carbons. And it's going to be 5-hexanol. That means on carbon 5, so this is carbon 5, you place an OH group, so 5-hex. Then on carbon 2, you have 2 substituents. One substituent is methyl, the other substituent is chlorine, chloro. So you can leave methyl. You can put CH3 for emphasis. And chloro. Now, as you can see, straight chain, it has 6 carbons, longest chain, and that's the longest chain. So in this case, we still have the same longest chain. So what is wrong? Well, the wrong thing is that this is alcohol. And so if it's alcohol, then we have to number it in such a way that hydroxyl group gets the smallest possible number. And that's number 2. And then methyl and chlorine will get numbers 5. So in this case, really it's the numbering that is wrong. So it should be 5-chloro, 5-methyl, 2-hexanol. Be very careful not to use computer to name this, because computer would name it 5-chloro, 5-methyl, hexane 2-ol, and that's not acceptable. That's a 0. Okay, why do we write ethyl and not methyl first again? Somebody already answered that. You should list substituents in alphabetic order. Question number 3. Okay, well, let me wait for it to start sharing. So question number 3, which of the following compounds exhibits hydrogen bonding? So that means intermolecular interactions. So you need to be able to determine which compounds exhibit London interactions only, which exhibit dipole-dipole interactions, and hydrogen bonding. For hydrogen bonding, if it's a compound that exhibits hydrogen bonding, it must be not only compound capable of hydrogen bonding, like the first one, triethylamine, but it has to form hydrogen bonds on its own. So basically hydrogen bonds it itself. So 2 molecules of the same compound have to form hydrogen bond. Here we don't have hydrogen attached to nitrogen. So this compound, triethylamine, is capable only of dipole-dipole interactions, not hydrogen bonding. So you eliminate that one. Triethylamine could form hydrogen bonding with hydrogen bond donor, like water or alcohol, methanol, ethanol, or primary or secondary amine. but not on its own. B is correct answer. That's the compound that exhibits hydrogen bonding. So this one exhibits hydrogen bonding. That's alcohol, propanol. And so that's correct answer, B. Because we have OH group, hydrogen attached to oxygen. So compounds that would exhibit hydrogen bonding on their own are compounds where hydrogen is attached to oxygen, nitrogen, or fluorine. Next, we have a molecule of 2-methyl-propane or isobutane, and that one exhibits only London interactions. Only London interactions because it's non-polar compound. So you determine whether compounds are polar or non-polar, and polar compounds will exhibit dipole-dipole interactions and possibly hydrogen bonding if you have hydrogen attached to oxygen, nitrogen, or fluorine. Non-polar compounds, only dipole-dipole interaction. And last compound is compound of phosphorus. So here we have hydrogen attached to phosphorus. So there is no hydrogen bonding. It does exhibit dipole-dipole interactions because there are polar bonds, but no weak dipole-dipole interactions, but nonetheless dipole-dipole interactions, but no hydrogen bonding because hydrogen is attached to phosphorus. It's not attached to oxygen, nitrogen, or fluorine. Oh, and just to let you know, I didn't post this anywhere. It's simply going to be part of the video that you're going to see because once you open and see the video, there are only 6 questions. So I don't see much purpose in posting this. I already posted practice questions, practice test. So there are 6 questions, and when you play the video, you can easily scroll down and see all the questions and do them, and also their answers as you go along. So that's how you answer questions about intermolecular interactions. Question number 4. Which of the following compounds is soluble in water? So water, you should know, exhibits hydrogen bonding, has OH group. So solubility, as I mentioned in the class, is basically dependent on thermodynamic properties, on whether system as a whole, when you mix different compounds, whether system as a whole will end up lower in energy. So whether process is thermodynamically favorable. So intermolecular interactions between molecules of solvent and those between molecules of solute are broken. That process requires energy, is not favorable. And then new set of intermolecular interactions, those between solute and the solvent are formed. That's favorable process. If energy released in the course of favorable process is equal, about equal, or higher than energy released required for unfavorable process, overall process will be favorable. That means that, as a rule of thumb, intermolecular interactions that are being broken, those strongest intermolecular interactions that are being broken, have to be replaced by same set of intermolecular interactions. So water exhibits hydrogen bonding. That means those interactions have to be replaced by another set of hydrogen bonding. That means that molecule that is capable of hydrogen bonding will be soluble in water. And so really you translate this question. That means that really this question is asking which of these molecules is capable of hydrogen bonding. Basically, you reduce it to previous question. The only difference is that this question requires a little bit more thinking, so it's more difficult for that reason. If this compound was not water, but was something that is capable only of dipole-dipole interactions, let's say some ether, like diethyl ether, then you would be looking here which compound exhibits dipole-dipole interactions. Or if it's non-polar compound, some alkane, we previously had an example of isobutane, then of course you'd be looking which compound is also non-polar, maybe another alkane or something like that, so that is non-polar. So exhibits only London interactions. Water, that means hydrogen bonding. And the first compound, alcohol, ethanol, exhibits hydrogen bonding, so that's correct answer. Of course, you should go over the rest just to double check. Next one is an alkene double bond that doesn't impart much of the polarity on the molecule. Effectively, the molecule is non-polar, so this would be soluble in some non-polar solvents and hydrocarbon London interactions. Next one is also, it has oxygens in the middle, so this in the middle of the molecules, this is class of compounds known as esters. So with oxygens present but no OH bond, this will be dipole-dipole interactions. And that means this molecule would be soluble in another molecule, another solvent that exhibits dipole-dipole interactions. And the same is the case for the last one. Carbon-bromine polar bond, so overall polar molecule, so will be soluble in something that exhibits dipole-dipole interactions. So in summary, first one, hydrogen bonding, so soluble in solvents that exhibit hydrogen bonding. Second one, London interaction is the strongest interaction, so soluble in solvents that exhibit only London interactions. And the last two exhibit dipole-dipole interactions, which means they will be soluble in solvents that exhibit dipole-dipole interactions. And of course, they are miscible with each other, soluble in each other, same set of interactions. See, so I said it's not posted anywhere. I don't see there are no more questions. So let's go back. Question number 5. How many carbon-methyl, equatorial carbon-methyl bonds are present in the conformation shown below? You may, from this conformation, you may already be able to count them. You look what are carbon-methyl. So methyl group attached to carbon of the ring. And you can see this is methyl, 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 methyl. There are 5 methyl groups. Of course, you would have to write down how many are present. Now, there are 5 methyl groups, but not all of them are equatorial. Equatorial are those that are around ring equator. So they are slightly down or slightly up, but about the plane of the ring, while those vertical bonds are axial bonds. So here you have actually 3 equatorial. Here's 1, 2, and 3. 3 equatorial. You may be able to figure out that by inspection of the model or of this drawing, or you may want to make a model from this molecule and then count them. And of course, there are 2 axial, just in case you're wondering. So for a total of 5 methyl groups. Now, question could have been slightly more difficult. You could have been asked about hydrogens. So how many hydrogens are equatorial and axial? Well, hydrogens are not shown here. So what you may want to do then is redraw this molecule on a piece of paper and then add hydrogens. And then once you see those hydrogens, count them. Or make a model and then from model count hydrogens. Again, I'm using Casey drawing program. It wouldn't show very well if I were to use pen and paper now and try to show those things. I'm trying to paste this. Okay. So for hydrogens, if we need to add hydrogens, simply if this is axial, then equatorial hydrogen is here. And then actually, there's another one. Each carbon that has methyl group will have 1 more hydrogen. If methyl group is equatorial, then hydrogen is axial. If methyl group is, what was here? If methyl group is axial, then hydrogen is equatorial. And this last carbon atom is actually CH2. It has 2 hydrogens, 1 equatorial and 1 axial. Okay. So we simply add these 2. And now you count them if you're asked about hydrogens. So axial hydrogens are those vertical, parallel to the edge of the drawing, edge of the paper. So 1, 2, 3, 4. So there are 4 axial hydrogens. and there will be 3 equatorial. So this is 1, 2, and 3. There are no more. 3 equatorial. Alternative way to come up with solution is to know that in cyclohexane there are 12 bonds, 6 axial, 6 equatorial. And so if you already figured out that you have 2 axial methyl groups and there are a total of 6 axial bonds, that means remaining 4 have to be hydrogens. And so you don't need to go through this process. You can just go just from what you have in the model, in the drawing as part of the question. If you were able to solve it by inspection, if by inspection you were able to figure out that you have 2 axial methyl groups, then you should be able to deduce that you should have 4 axial hydrogens, because there are a total of 6. And if you figured out that you have 3 equatorial methyl groups, that means remaining 3 are equatorial hydrogens. Okay. Any questions before I go on to the final one? Okay. So what is the hybridization of each indicated carbon atom? So for carbon, oxygen, nitrogen, hybridization is sp3, and then this is 3 minus number of p and pi bonds. So for A, hybridization is going to be, you have only single bonds. There are no empty orbitals. Empty orbitals will be p orbitals, and there are no pi bonds. Those will be double or triple bonds. Double bond has 1 pi bond, triple bond 2 pi bonds. So this is hybridization sp3, and that's how you should write it on the test. You don't need to write down superscript or sp in italics or anything like that. Just write it like this. Now B, this carbon is attached to nitrogen with a double bond. So double bond has 1 pi bond. So 3 minus 1 will be 2. So hybridization is sp2. And that's it. You will not be drawing any structures, but if you are drawing formulas, although actually it just occurred to me, I was going to tell you about double and triple bonds, but it just occurred to me that this is something we are covering in the chapter 8. So it will be test 2. So on this test, you will actually not be drawing double and triple bonds. But let's say you're asked, let's do question 7. To draw a formula of 2-bromopropane. So how are you going to draw it? It's going to be CH3, CH, Br, CH3. So don't do any superscripts, anything else. That's it, that's the formula. 3 carbons, 1, 2, 3. On second carbon there is bromine, and that's it. By the way, it may not be in your interest to even try. You can do this. You can simply draw this formula in a Word program like this, and simply use subscripts, and that's it. You copy this. So you copy this, Control C, and for the exam in Canvas, Control V, and it will appear there correctly with all subscripts and everything. Why it's not in your interest? First, you don't get any better grade. you waste time doing that, and you should be doing your exam. And what happened to last fall was one student made a mistake and did this copy and paste and did it like this. So you see what he did. He put CH and then 3, did subscript, and then typed everything else as a subscript. So, okay, I saw that and I know its correct answer. And I see he was trying to show how good he is, that he could do subscripts. It backfired. I didn't take any points off initially for that. I said initially. I gave him initially 4 grades. As I continued grading, I found another student, and it was identical. So what are the odds that 2 students are going to independently, the 2 students are going to try to insert subscripts, which they don't need to, and that they're going to make identical mistake. So of course I compared their exams. They were a pretty good match, and so this did not work out very well for them. So keep that in mind. Really do what you are asked, and you will do well. As I said, I know the time for this exam was a little bit shorter than ideal, and so I have made the exam a little bit easier than usual. So exams are a little bit easier. So keep that in mind. Basically, I took into account how much time you had to prepare, that this is accelerated course. And so you individually may not find exam easy, and you may be kind of a little bit depressed. I thought exam is going to be easy. It was really hard. But I can assure you that exam is easier compared to usual organic 1 first exam. Also, I have covered quite a bit as part of practice. I told you during my lecture, study this, study that, and so on. And then when you take an exam, you may find there are no questions on it. And you may feel, well, why he emphasizes this so much and why did I study? Obviously, you may need that material to understand material that is coming up later in the course. And the other reason why it's there is that we also have a final. And final exam is cumulative. And so questions that may not have been now on the test, maybe on the final. So keep that in mind. There is no special practice for the final. So when you are preparing for the final, you should look at these old practice tests, old practice questions. They are preparation for the final. There is nothing else, nothing new, nothing special for the final. There will be chapters 12 and 14 that are not tested on any other tests, that are tested on the final, but I will explain that when it comes. These chapters 1 through 11, they will be, there is nothing else, no additional practice. That's everything I plan to cover. Exam is 6 p.m. tomorrow. So before I let you go, are there any final questions? Are these practice questions about the same level of difficulty as the questions on the exam? Yes, they are. For the practice test 1, maybe some are a little bit more difficult, but it's good representation of what would be on the exam. From chapter 4, how much do we need to know about the conformation of cyclohexane? You need to know a lot. You need to know both and chair conformations, their energies, and you need to be familiar with substitute cyclohexanes, so mono and disubstitute cyclohexanes. I don't really understand how you did the hybridization. Go to textbook and page, it's directly from the page 27. So it's simple formula. It's simple formula, and you just apply that formula. The only, I misspelled hybridization. The only thing is that you need to be able to recognize p and pi bonds. So that's a trick. Other than that, formula is 3 minus whatever number there is. Do we need to know a twist boat conformation of cyclohexane? Well, you do, but there is not much special about it. You just need to know it's a boat that is twisted. I mean, It's trivial extension of both conformation. You just need to know it's a little bit more stable than both conformation. So not much more there. So basically, this is both conformation, okay? And then twist both is just a little bit twisted. That's it. So these two bonds are not parallel as in both, they're a little bit twisted. And that's all. Are there ever free electron pairs in a p orbital unhybridized? Well, yes, but you will only learn that in the second semester organic 2, so I won't be teaching that. My colleague Elijah Saint-Germain will be teaching that. For this exam, you should assume that answer is no. But yeah, there are, and that's organic 2, so hopefully we'll make it by then. You will see organic 2, unfortunately, is much more difficult. And I don't envy Elijah. Elijah is an excellent instructor. I'm sure he'll do an excellent job teaching you, but that's not my job. So in a way, I guess I'm getting a little bit easier part of the work this summer. From chapter 3, exercise 8. Let's see. Which of the following becomes more soluble? Oh, that's actually, sorry. That's in chapter 3, but that's actually, I made a mistake by putting it in chapter 3. That's chapter 5. That's chapter 5 material, so don't worry about that one. So exercise 8, which is more soluble upon addition of acid and base, those are acid-base properties, and you should know chapter 5 to answer that. So that won't be on the test, and you're not expected to know that now. I made a mistake because it was a solubility question. I put it in 3, but actually you need acid-base properties to answer that. Okay. It's good to notice that at least you're studying, but you won't need it now, so don't worry. Don't worry too much about this test. Okay, any other questions? Okay, last call for questions. Okay, so the processing of the video takes a while, and the shorter the video, the shorter the processing, the sooner I will be able to post it. So I'm going to stop recording right now.